Hello everyone. In this video, we're going to be solving a logarithmic polynomial, a mixture of two different things type of equation. We have x plus ln x equals 1 minus e divided by e, and we're going to be solving for x values. We're going to look at a function, its derivative, so we'll do a little bit of calculus, define a special type of function, and we're going to be taking a look at the graph at the end, which explains a lot of things. All right, let's get started. First off, I want to separate the two numerators. So I want to write this as x plus ln x equals 1 over e minus e over e, which is 1. And then 1 can be written as ln e. And with the minus sign in front of it, we can basically put this as e to the power negative 1. We have this power rule, but you can use it either way. So from here we get x plus ln x, and I'm going to write this as 1 over e plus ln 1 over e, or e to the power negative 1. All right? Now, looking at these two equations, what are you thinking, right? Well, if x is equal to 1 over e, then ln x is going to equal ln 1 over e. So do you think x equals 1 over e is a solution? Does it work? Yes, it does. But the million-dollar question is that the only solution, or are there any other solutions? So let's go ahead and take a look at this function first, and we're going to change it up a little bit. We're actually going to be looking at three different kind of functions here, I think, right? Anyways, let's proceed. Suppose f of x is equal to x plus ln x. In order to understand how a function behaves, especially from a maxima-minima perspective, we need to differentiate it. See if it has any horizontal tangents. When you differentiate x, you get 1. The derivative of ln x is 1 over x. And notice that if x is positive, and guess what? X needs to be positive because we have ln x. In order for that to be well defined, for reals, x must be positive. Complex numbers, it's a different world, but x needs to be positive. Therefore, this expression is also going to be automatically positive, because if x is positive, 1 over x is also positive. And 1 plus 1 over x is definitely more positive. Well, there's nothing more positive than any positive number, but as you can see, it is going to be positive. Okay, great. So what is that supposed to mean, though? If the derivative of a function is positive on an interval, which happens to be the whole thing in this case, what is going on? It just means that when you have a function and you're drawing tangent lines, they all have positive slopes. This basically means that our function is going to be increasing. Make sense? That's what it means. So f is increasing. F is increasing. And what is that supposed to mean? We'll talk about that in a little bit. But f is always increasing. Now, let's go ahead and do this. We're going to need to use e here for our alternative approach. I wouldn't want to call this one first, second, third method, but I'll put it all together, okay? So let's go ahead and use e, Euler's number. Some people say it's not Euler's number. Whose number is it then, right? I mean, it must be Euler's number because Euler is awesome. So let's go ahead and do e to the power both sides. Remember, x plus ln x was equal to what? 1 minus e over e, but let's write it as 1 over e minus 1, because we separated them into two pieces, right? Like that. Should I use this version? No, not really. This is going to be good enough. All right, now we have something interesting on the right-hand side, and on the left-hand side, we can go ahead and separate them. Let's go ahead and separate these. E to the x times e to the ln x equals e to the 1 over e divided by e. I could also write it as times 1 over e. Same idea. Make sense? Okay, so doing a little bit more work here is going to give us, this is x, right? As you should know, we get x e to the x, which kind of brings us closer to our special function. And this guy over here can be written as 1 over e times e to the power 1 over e. Okay? Do you see what I see? We have x e to the x, so we're going to go ahead and use Lambert's W. Lambert's W function is basically, can be defined as follows. We have a function that takes te to the t as an input and outputs t. If you kind of switch these around, you're going to get the inverse Lambert W t equals t to the t. In other words, if you call this like a g of t, then our function g of t is going to be te to the t, and Lambert's W function is just going to be its inverse. Make sense? So this is Lambert's W function. It basically solves these kinds of equations. And we're not going to look at the graph of Lambert's W function, which I shared with you before, but I'm going to show you a different graph, okay? But anyway, so here's how we proceed with this equation then. We got to this point, and we're going to do Lambert on both sides. W x e to the x equals W 1 over e times e to the power of 1 over e. You might be asking, like, isn't this clear that x is 1 over e from here? Why do you need Lambert? Why do you need to complicate things, right? Well, here's the thing. How many solutions are you going to get? That's determined by this process. Anyways, from here, we obviously get x equals 1 over e, and that seems to be one of the solutions. Now, let's go ahead and check the graph of our function, which is x e to the x. But before that, let's go ahead and do a little bit of calculus, a little bit more. Bear with me. If, and I think I defined it as g, right? So if g of x is equal to x e to the x, then you can basically differentiate both sides. That's going to give you the derivative of x times the second function plus the derivative of e to the x times the first function. And if you take out e to the x, you're going to get 1 plus x. And if you set this equal to 0, the only x value, real x value, is going to be x equals -1. By making a table of x, g prime, and g, you're going to get the following. -1 is going to be a solution for the derivative. And if x values are greater than -1, like 0, for example, our derivative is going to be positive, and then otherwise it's going to be negative. So our function is going to be decreasing first and then increasing, making a minimum point at -1. X equals -1, obviously, or g of -1 is going to give you x e to the x. So it's -1 times e to the power of -1, which is -1 over e. Make sense? Okay, now, here's the thing. That kind of gives us a maxima and minima, whatever, and now we're going to look at the graph. But before that, let's go back here and see what that value is going to look like. So we had this number, and what does this number look like, right? Well, this number is approximately 0.531. Now, pay attention to that value. I'm going to call this y, and you'll see in a little bit why it's important. Why is y important? So 0.5-ish, right? Okay, let's go ahead and take a look at the graph now, and hopefully things will be more clear. Okay, so here's what the graph looks like. The graph of x e to the x. Had a lot of spaces. Anyways, notice that it has a minima, as we talked about it already, -1, -1 over e. And then I wanted to give you a little band between -1 over e and 0, because what happens is, if our y is on that interval, then we're going to get 2 intersection points, as you can see, right? So if any horizontal line that you draw within the band is going to have 2 intersection points. But our value, which is this one here, is going to be actually greater than that. Therefore, we're going to have a single solution, which means x equals 1 over e is the only solution to our equation. And this brings us to the end of this video. Thanks for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.